This video is where we finally get to introduce the connection between the two branches of calculus. And so what we've been doing so far in this course has had to do with the derivative, and that is the branch of calculus called differential calculus. And we're starting to learn about the other branch of calculus called integral calculus. And what ties these two branches of calculus together is the fundamental theorem of calculus. And so let's just recall where we've been in this class when we were looking at derivatives. The derivative is the central theme of this branch. And if you remember how we got there by considering a couple of problems, the tangent problem and the velocity problems. We looked at these problems and it helped us understand and develop the concept of the rate of change. And what was involved in all of this was limits. Limits were involved in this branch. And so what we're going to find is, as we look at the branch of integral calculus, there will be a couple of problems that we consider, and today we're going to be looking at the area and distance problems. And when we look at the area and distance problems, it's going to help us develop the central theme of integral calculus, which is called the definite integral. This is what mainly is centered around the integral calculus branch. And what is common to both of these branches is that they both involve limits. And so we're going to see how this goes. Let's see how they're connected. Now, the fundamental theorem of calculus is what connects these two branches together. This relates the integral to the derivative. So it is very, very important. Okay, it also greatly simplifies many problems. So we're going to see that. So as we get into this, let's just consider the area. And so a long time ago, when people were learning how to figure out area, if you had like a regular figure, maybe some polygon, something like this, and you've done this probably in geometry, you could simply divide this into different triangles and then find out the area of this triangle and add it to the area of this one and the area of this one and the area of this one. Because we know how to find the area of a triangle, we could just add all that up. But the problem becomes a lot more complicated if you're trying to find the area of a smooth curve, such as a circle or something like that. And so what they did a long time ago was take the area of a known figure. We could say, okay, this triangle can approximate the area of the circle. But what if we try a square, we add another side, it fits the circle better, and there's less of this extra area that's not accounted for. And what if we increase the number of sides of the regular figure to 5? It gets a closer estimate, and 6, it gets a closer estimate, and 7, it gets a closer estimate. And as we keep increasing the number of sides of the regular polygon that we approximate the circle with, we get a closer and closer fit to the circle. This is known as the method of exhaustion. And it was used long ago to approximate areas of things we didn't know. And so we're going to do something similar as we look at the area under a curve. So let's just suppose that we wanted to know the area under a curve. And so here is some curve, only it's going to be a nice regular shape. If we have to approximate the area under something like this, that is very easy because this is a big rectangle. That's not a problem. Or if we had to approximate the area under something like this, if we had, if this was straight line and this, we could say, okay, this would be, if this is, we could say this is a triangle, we could figure out this guy's area, and then we could add this guy's area and this guy's area. So it's not that big of a deal if it's a regular shape. But if it's a curved shape, then it becomes a bit more tricky. So this is what we're going to learn to do. Here is, let's just consider this curved figure. Let's see. What if we've got something that does this? Okay. And we want to approximate the area under this curve from this point A to this point B. All right. So we want to know the area of this region right here. What we can do is divide this region up into known figures, into something that we can find the area of, and that provides an approximation of the area. So let's see, we could divide up this, we could split A and B into little sub-intervals. We could say, let's split this up into little sub-intervals. Let's see. And so what we could do is we could draw little rectangles underneath here. Okay, and so we'd have to decide the width. We could decide what the width is in between these. These will be regular intervals. So like this distance here, between here and here it's the same as it is between here and here. Okay, so that's the width of our rectangle, and then the height. So sometimes the height is determined. We might say, let's look from the left, L sub n. Let's figure out the area starting at the left endpoint. So that what that means is right here, here is one triangle. So if I pull this rectangle, if I pull this one rectangle out, I'm going to let this side of the curve, the left side, determine the height. And then so this is the first rectangle. Then let's add it to the area of this second rectangle, and we're going to let the left side of this, where it hits the curve on the left side, determine the height. And so we're going to go through here, and everywhere there's a left, where the rectangle hits the left side, we're going to let that determine the height of our rectangle. So on the third one, here's where it hits the curve. This is going to be the height. This is going to be the height. This is going to be the height. And this is going to be the height. So we let the left side determine the height right there. And so we see that right here there's a little bit of overestimate right there because it's bigger. But it's an estimate. That's what you get right there. So that's how you would draw it there. And you could add up the area of this guy plus this rectangle plus this one plus this one plus this one plus this one, and that would give us an estimate of the area under the curve. So let's go again. Here's another way you can think about that. What if I'm trying to draw a similar picture? So if it doesn't look exactly the same, just know that I'm trying to draw a similar figure. So what if we've got this one? So whoops, let's just pretend it looks like that. Okay, so we still want to know from A to B, only this time I say let's let our rectangles be determined from the right side, R sub n. All right, so we're still going to split it into these subintervals. 1, 2, 3, 4, 5. Okay, but this time we're going to let where it hits the curve on the right determine that. So if we go from the right side, let's just say this will be where it hits the curve from the right, and we'll go across. And this is where it hits the curve on the right side. That will determine the height. And this is where it hits the curve on the right side, and that will determine the height. And then this one right here, that determines the height of that one. And this is where it hits the curve, and that determines the height. So this time, we let the right side, these points right here, determine the height. And you can see in this picture, there's a little bit of area under the curve that is not accounted for. So in this particular example, the estimate of the area when we let the right endpoints determine the height is going to be an underestimate. This is an underestimate. estimate of the area. In this particular case, the rectangles were bigger, higher than the actual curve, so this would be an overestimate, is what we get here. All right. Sometimes they say, well, let's just determine the height from the midpoint of our rectangles. Okay, so you could also have this same picture here. So again, I'm trying to draw the similar picture, something that looks like this. Okay. And say we're going to go from A to B, and we've got these little subintervals. 1. Got these little subintervals. But they say, okay, let's let the midpoint of the subinterval determine the height. So let's see. If this is where the rectangle is going to be, okay. Where does the midpoint hit? The midpoint hits right here. We'll let this midpoint determine the height. How about this guy? Where's the midpoint? Right here. This will determine the height. Go to the midpoint where it hits the curve. Let that determine the height. Halfway in between here, that will determine the height. Halfway in between here, that determines the height. And halfway in between. So that time we let the midpoint determine. That looks like, oh, that looks like I missed the midpoint. This looks like where the midpoint ought to be. The midpoint determined the height. And so that's another way you could do it, the midpoint estimate. Okay, so I wanted you to get an idea of how to draw these rectangles, because now we are going to calculate the area of something. So we are going to do it 4 times. So I'm going to split this video up into 2 or 3 just so it doesn't get too long. So I'm going to pause this and start another one.